Day 40, page 888, problem 49. This one looks a little weird on a couple of levels. Well, at least one level is this fish. You know, fish never, unless they're dead, they don't have that sort of position in the water. But what's interesting here is if you actually were in water, and then you kind of think about this for a few minutes, and went through this particular demonstration, and you had really, really calm water, if you looked up, basically you can see a great angle view of the world. As you see here, the fish is seeing a 360, well, 180 degree panorama of the world outside the water, because whatever light is coming into his eyes is what he sees, and he doesn't see things where they're really at. He thinks he sees the bird. He thinks he sees the bird right up here, this bird. Okay, that's where he thinks he sees it, where it actually is, where it is the darker version. But once again, to kind of extend this, if he was looking up, what he basically would see is kind of like a round portal. If the water was really calm, he'd see a round portal through which he would see essentially the panorama of everything outside the water. That's kind of the last part of this problem, explaining what is happening and compute the cone angle. Well, so let's do this. For example, to get the cone angle, the key is the extremes. So what we have here is the situation where light is coming over here and into his eye. All right, you can do this way or the reverse way. But if I draw my normal right there, all right, in other words, if my angle of incidence is 90 degrees, which I theoretically can have, or really technically can't have, but I can compute that. This is where basically we're at the critical angle right there. So that's 90 degrees. And then we're looking for theta sub 2, because we're dealing with water, which has an index of refraction of 1.33. And the same is true from the reverse side. I have light coming in this way into the guy's eyes. And, well, let's finish this off. So it's the same thing on this side. If you have a 90-degree angle of incidence, theta sub 2. So using Snell's law, n sub 1 sine theta sub 1 equals n sub 2 sine theta sub 2. I mean, basically we're calculating the critical angle in reverse. So n sub 1 is air, 1.00, sine of 90, equals n sub 2, which I believe water is 1.33, sine theta sub 2. So calculate theta sub 2. Let me do that. And that is 49 degrees. All right, so if that's 49 degrees, now let's do the geometry here. If I now draw this line straight down, that also means by alternate interior angles that this is 49 degrees. Boy, that would be alternate interior with theta 2, and this is 49 degrees. Each of those 49 degrees are half the cone. In other words, if you double that, the cone angle is 98 degrees. So one or two more comments here. So basically what he sees is if he draws a cone looking up, that will define the base of the cone will be a circle. And through that circle, he will see the outside world 180 degrees, actually all the way around, 360 degrees, but horizon to horizon, which is 180 degrees, but in a full circle, 360. And beyond that circle, he would see reflection of anything inside the lake, because there would be total internal reflection coming into his eyes from anything beyond that. I'll just draw you one of these. I'll use blue. So in other words, there's one example of light coming from underneath the water, because he can't see anything else from above the water. It's already been delineated by the diagram. But if I draw the normal right here for this particular reflected ray, that's total internal reflection. That angle right there, I'm going to call it theta 3, theta sub 3, is bigger than the critical angle. It's bigger than 49 degrees. So you're going to get total internal reflection. That would also be theta sub 3. total internal reflection. So anything beyond that cone of 98 degrees, as he's in that awkward position of looking straight up like that, he's going to see reflection of things underneath the water, or in his world, his watery world.